Hi, everyone. So today I'm going to talk to you about matching in the streaming model. So let's start by quickly reviewing the model. So in the streaming model, the size of your input is much, much bigger than the memory on your machine. And so the input arrives as a data stream, and the algorithm gets to make a single pass over the data stream, and it has to figure out various information about the input while only using a small amount of working space. So in classic problems like frequency estimation or heavy hitters, you really only need like polylog working space. But in graph algorithms, you're typically going to need somewhat more space. So here the model is pretty much the same. Your graph arrives as a data stream, and in particular, the edges arrive one at a time. But now you're allowed to use n polylog n working space. So basically, if your graph is very dense, then you might have n squared edges in the graph, but the space you're allowed to use is only proportional to the number of vertices. And the reason that we allow n space is, first off, there are lots of lower bounds for many problems showing that n space is necessary. And also, secondly, for many problems, the output itself is going to have size n. So that's how much space you need to return the output. And that's going to be true of the problem in this paper as well. So in this talk, the goal is at the end of the stream, you have to return an approximate maximum matching, which might have size as large as n, so you're going to need n space to return it. Okay, so let me talk to you about what's known. So the standard streaming model is the adversarial one. And here, basically, the graph is worst case and the ordering of the edges is worst case. And there's a trivial upper bound for this problem, which is you just compute a maximum matching. So you just go through the edges one at a time. And if you ever see an edge where both endpoints are unmatched, then you just add that edge to your matching. And that gets you a 1/2 approximation. And this is actually the best that's known. And beating this bound is one of the main open problems in the area. So even beating it by a little bit would be a huge breakthrough. The only lower bound that's known is that if you want to do better than a 1 - 1 over e approximation, then you're going to need more than n polylog space. But we really don't know what the right answer is between 1/2 and 1 - 1 over e. Okay, so to make progress on this problem, people have turned to a slightly relaxed model known as random order streams. So here, the graph is still worst case, but the ordering of the edges is a random permutation of the edge set. So the adversary doesn't get to pick the order, only the graph itself. Now the goal is to find an algorithm that outputs a good matching with high probability. So let me talk about what's known. So previous work, there's actually been a lot of work done on this problem. I'm not going to go through all the results, but I do want to highlight that basically first the goal was just to beat 1/2 by any margin at all. But over time, we really made significant progress over 1/2. And in particular, there are two results I want to highlight. So the first is that you can get a 0.545 approximation or 0.6 for bipartite, and you really only need n polylog space. So this is a very recent paper. And then there's another incomparable paper which gets a better approximation, but the space usage, although subquadratic, is not n polylog n. So this isn't really the semi-streaming model. So one thing I want to point out about both of these results is, on the one hand, they improve upon the 1/2 approximation adversarial streams. So they do suggest that random order streams are easier than adversarial streams, but they don't definitively prove that, because neither of these results actually beats the adversarial lower bound. Right, the first result, the approximation ratio is too low. The second result, the space is too high. Okay, so this leaves the open question, can you actually show that random order streams are provably easier than adversarial streams? And we answer this in the affirmative. We show that you can get a 2/3 approximation in n log n space. So this is basically the best of both worlds of the two results above, and it is strictly better than both those results. And it's also the first result to go beyond the adversarial lower bound. Okay, so let me talk about how we achieve this result. So this is a bit of a tricky talk to give because on the one hand, the result is very simple. It's like a 10-page paper, all proofs included. But the result relies heavily on this previous technique called the EDCS, and it really gets into the nitty-gritty details of how to compute the EDCS in the streaming model. And I won't really have time in this talk to give you all the necessary background, but I'm going to sort of try to give the basics of how the EDCS worked, and then try to talk about how we integrate it into the streaming model. So let's start with the background. So first, just simple notation. For any graph G, I'm going to let mu of G be the size of the maximum matching in G. So what's the very high level approach? Well, as we go through the stream, instead of trying to just directly compute a matching, what we're going to do is we're going to compute a subgraph H, which is slightly larger than a matching, but has the property that this subgraph contains a large matching. And we're just going to explicitly store the whole subgraph. And then when we get to the end of the stream, we'll just compute a maximum matching in the subgraph. So let me talk about, sort of contrast our approach to previous algorithms. So almost all previous algorithms for this problem relied on an augmenting path-based approach. So the idea is basically this. If you have a maximal matching, that gets you a 1/2 approximation. If you have a matching with no augmenting paths of length 3, that gets you a 2/3 approximation. And the idea of these algorithms was to find a matching that is maximal and gets some of the augmenting paths of length 3. And the vague intuition is that basically if the edges of the augmenting path arrive in just the right order, then you'll be able to compute it. And because the stream is random, some of them will arrive in the right order. Okay, so there was one result which was different that had nothing to do with augmenting paths, and they instead computed a subgraph which is called an EDCS of G. And we're going to follow this approach, but whereas their algorithm used n to the 1.5 space, ours is going to use only n polylog space. So now let me talk about the EDCS. So you have a graph G, and now I'm going to say that a subgraph H is an EDCS if it has the following properties. So the subgraph is going to be an edge subgraph. So it's going to have the same vertices as the graph G, but only a subset of the edges. And we're going to have this parameter beta. Just think of it as a large constant. So now H is an EDCS if, firstly, for any edge in H, any edge in the subgraph must satisfy the following property. Look at the sums of the degrees of its endpoints. And when I talk about degrees, I am always talking about degrees in H. I'm never talking about degrees in the original graph, always degrees in the subgraph. So basically, the degree of that edge is just all the edges incident to it in H. And that number has to be at most beta. The second property is now if you pick a target edge which is in G but not in H, and again you look at its edge degree, then there's a lower bound that has to be at least beta minus 1. Okay, so any graph that satisfies these properties is an EDCS. I recognize that just by looking at these properties, you're not going to have a clear intuition for what they're doing, why these are useful properties. So I won't have time to go into the details, but let me sort of give a quick intuition, which is that what we really want is a subgraph H where all degrees are equal to beta over 2. So it's a regular subgraph. So note that if we had such a subgraph, it would definitely satisfy all the properties because all edge degrees would be beta, all properties would be automatically satisfied. And moreover, such a graph would be really good for us because we know that a regular graph contains a perfect matching in bipartite graphs and a 2/3 approximation in non-bipartite graphs. So if we could find such a regular subgraph, we would be in great shape. Now, of course, some graphs might not contain a regular subgraph. And so these properties are sort of trying to push you as far as possible into getting a regular subgraph. So that's the vague intuition. Okay, the second thing I want to point out is that the definition is very simple in the sense that it's just a bunch of local constraints on each edge. And this is going to make it easy to work with in a bunch of ways. So let me tell you about what was already known about the EDCS. So first off, it's very easy to see that it's always going to be sparse because property 1 basically ensures that the degree of every vertex is at most beta. So the number of edges in the subgraph is going to be at most n beta. Beta is a large constant, so it's a very sparse graph. Secondly, you can show that the EDCS is always going to exist for any beta. And finally, the main theorem is that any graph which satisfies these properties contains a large matching. All right, so we're going to crucially rely upon this theorem. So let me tell you a bit about the history here. So basically, all these basics of the EDCS were developed by me and Cliff Stein in 2015 in the context of dynamic graph algorithms. So we weren't even thinking about the streaming model. But then later, me and some co-authors showed that in fact you can compute an EDCS in random order streams. And this is how we got a 2/3 approximation. But we needed n to the 1.5 space to do that. And in fact, it's unclear how to reduce the space. So if you actually want to explicitly compute an EDCS, I'm not sure how to do that in less than n to the 1.5 space. Instead, our approach is going to do two things. First off, we're not going to directly compute an EDCS. Instead, we're going to compute a relaxed version of it. And second off, we're going to use a very different construction, which much more aggressively uses the randomness of the stream. Okay, so before talking about how we compute an EDCS in the streaming model, let me give some intuition by showing how we compute it just in the standard setting where you have no space limits, the whole graph is in memory. So again, up top, I have the definition of the EDCS. And here's the construction. You're going to look for an edge that violates one of these properties, and then you're going to fix it. And then you're going to look for another edge that violates one of the properties, you're going to fix it, and you're just going to keep doing this until there are no edges left to fix. All right, so how do you fix an edge? Well, let's say that you find an edge in the subgraph that violates property 1. Then you can fix it by just removing it from the subgraph. Because note that once you remove it, it'll now be under property 2, and I claim it'll now satisfy property 2. And the reason is that before you remove the edge, so you know that the reason you removed it is because it violated property 1. So the edge degree was at least beta plus 1. Now you remove it from the graph, so the degrees of both of its endpoints fall by 1. So now the new edge degree is at least beta plus 1, so it satisfies property 2. Similarly, if you find an edge that's not in the subgraph, whose edge degree is too small, you can always fix it by just adding it to the subgraph. So that's the whole algorithm. You just keep going, and if you find an edge that violates, you just add it or remove it from the graph, and you keep going. So the only issue is that fixing one edge might cause new edge violations. So you might have to sort of keep doing this for a while, but we can show that it always terminates. Within n beta squared edge fixes, you always terminate. And the intuition is basically this, that every time you fix a violating edge, you're in some sense getting a little bit closer to a regular degree graph. And in fact, after n beta squared fixes, you're guaranteed to have precisely a regular degree graph. And then all edges are automatically satisfied. So that's why you can have at most n beta squared fixes. Okay, so let me give you an example of this cascade of edge violations, because that ends up being very relevant to the streaming model. So here you have a graph. The black edges are in the subgraph, the dotted edges are in G, but not in the subgraph. And you can notice that every edge except for the top one satisfies our properties. So in particular, all the solid edges that are in H, their edge degree is either 4 or 3, so it's good. So I'm setting beta equals to 4 here. And now similarly, the dotted edges, their edge degree is always 2 plus 1, so it's 3. So again, those are good, except for the top edge. The top edge has edge degree 2, which is less than 3, so it's violating. So what will our greedy construction do? Well, it's going to fix that edge by adding it to the subgraph. So now this increases both degrees by 1, and you can see that top edge now satisfies property 1, everything is good. But now, because you increase degrees, some edges are going to start violating property 1. In particular, those edges, their edge degree is now 5, which is bigger than 4. So you have to fix one of them. So you pick one to fix, and now you're going to remove it. This lowers degrees, and it actually fixes the other edge as well. But now you have a new violating edge, so now you have to add that to the subgraph. You fix it, and you can check that now you have an EDCS. All right. So now let's think about what would happen if we tried to mimic this in the streaming model. So first, let me say this. We have these two EDCS properties, and we're always going to just explicitly store the subgraph H. And now what I want to note is that from the streaming perspective, these two properties are actually pretty asymmetric in the sense that the first property is very easy to maintain because it only depends on the edges in H. You don't need to know anything about the edges outside of H to maintain that first property. But for the second property, you do have to know edges outside of H, which makes it much harder. For the first property, at any time, you could just run a simple subroutine, which is going to remove all edges that violate property 1. Just go through H and remove all bad edges. So it's really property 2 that we're going to have to worry about. So now let's think about how the algorithm works. So we're going to set beta to be a large constant. And our goal is we're just going to store a beta EDCS. And what we'll do is when we see a new edge, if that edge violates property 2, then we're going to fix it by adding it to H. And then we're going to remove all edges that violate property 1. Okay, if you see an edge that doesn't violate property 2, well, then it's not violating. There's nothing you should do. So you just go to the next edge in the stream. So what is the problem with this algorithm? The problem is that if you see an edge and it doesn't violate property 2, then you just forget about it forever because it doesn't violate property 2, so you don't need to add it to H. But now let's see what can happen. So it's going to be the same bad example as before, but I'm just going to think about the order in which I have my edges. So this you can check as an EDCS. Now let's say that this is the next edge I see in the stream, this green edge. So that edge isn't violating. So you don't add it to H. You just leave it out, which means you forget about it forever because you can only afford to store the edges in H. But now let's say that you add this top edge. Well, that is violating, so you have to add it to H, and as before, this leads to a cascade. You have some violations. You have to remove those. You remove one of those bad edges. But now the middle edge is violating just as before, except you don't know that because you're not storing that edge in memory, so you have no idea that you have a violating edge. So the issue with this naive construction is you can end up with a lot of violating edge that you have forgotten about, so you don't know they're violating, so you can't fix them. So you don't end up with an EDCS. All right, so let's talk about how to fix this. So first, just some basics. We're going to split the stream into an early part and a late part. The early part basically contains an epsilon fraction of the edges, and the late part contains all the other edges. And the first basic lemma I want to say is that because our edges arrive in a random order, and the late part of the stream contains most of the edges, the maximum matching in the late part is going to be almost as big as the maximum matching in the whole graph. So for the probability to work out, you need the matching to be at least log n, but if the matching is smaller than log n, the problem is really easy anyway. So we can assume that the matching has size at least log n. So informally, rather than trying to maintain an EDCS of the whole graph, we're going to try to maintain an EDCS just of the late part of the graph because we know that that's good enough. Okay, and now two simple definitions. So this was our definition of an EDCS, and basically note that we have two types of violating edges. We have edges that violate the first property. I'm going to call those overfull because their edge degree is too high. And we have edges that violate the second property. I'm going to call those underfull. And here's something I want to say, which is that, actually, let me go back. So let's say you have a graph that contains no overfull and no underfull edges. Then it's an EDCS, right? Just by definition, it contains no violating edges, so it's an EDCS. Okay, and now a slightly more refined observation. Let's say you have a graph that contains no overfull edges. And also, it contains no underfull edges in G late. Then I claim that this graph contains 2/3 approximation to the maximum matching in G late. Because the idea is that you have no violating edges in G late, so your graph is going to be an EDCS of G late. And finally, we need one generalization of this. And this is going to be a key claim we're going to rely on, which is, let's say you have some subgraph and has no overfull edges, but it does have a small number of underfull edges in G late. Well, then H itself might not contain a large matching because it has these violating edges. But the claim is that if you take H and the violating edges together and you just look at that all of those edges together, then between them, they're going to contain a large matching. And the intuition is basically just, we know that edges that aren't violating, edges that are not in H and aren't violating, we don't need them to have a large matching, right? That's what the EDCS tells us. Just the EDS itself should be enough. So basically, the only edges that are a problem is the violating edges. Those are the only edges that we might need to use. And so if you look at all the violating edges plus the subgraph together, they're going to contain a large matching. All right, so we're now ready to give a very high-level approach of our algorithm. And the algorithm is going to run in exactly two phases. And the first one is going to deal with the early part of the graph. The second one is going to deal with the late part of the graph. And most of the work is actually going to occur in the early part of the graph. So here's our goal at the end of phase one. So you see I marked some of those x's green. So basically you go through the edges in G early, and you want to construct some subgraph H, which has the following properties. First off, H should have no overfull edges. And second off, there should be relatively few underfull edges in the later part of the stream. So basically, H is not quite an EDCS. There are some violating edges in G late, but there should be few of them. So I haven't shown you how to actually achieve this, but let me show you why, if we could get this, then it would be enough. So here's the algorithm. So after phase one, here's what we would do. The algorithm would just pass over all of G late and collect all the underfull edges. Note that there's no cascade of violations here or anything because we're not changing H. We're literally just going through each edge, looking at its edge degree and checking whether or not it's large enough. So it's very easy to just gather all the underfull edges. Now we use our key claim. We have our subgraph. We have all the violating edges. So if we put them together between them, we're going to be able to find a large match. All right, so the key part is really phase one. So from now on, I'm going to focus on phase one. How do we get these properties? Well, the first thing I want to point out, similar to something I've said before, is that the first property is very easy to maintain. Because recall that by the definition of overfull, it really only depends on the edges in H. But we're always going to explicitly store all the edges of H. So we can always tell if some edge is overfull. And in particular, we're just going to maintain the invariant that we never have any overfull edges. And we can do that just because basically every time we change H and there's any danger of having overfull edges, we just run the subroutine to remove overfull edges. All right. So the hard part is the second property. And in particular, note that in order to get the second property, we must take advantage of the randomness of the stream. Because we're computing a subgraph H in G early, but the second property relates to edges in G late. But we haven't even seen the edges in G late. So the only reason we can say anything at all about the edges in G late is because the ordering is random. And so G early actually tells us information about the graph as a whole. And in particular, it's going to tell us information about G late. All right, so let's talk about how to do phase one. So we're going to go through the early part of this stream, but we're going to split it into segments. And each segment is going to have size like m over n, which in particular is less than n, which means you can store all the edges belonging to one segment. So upon the arrival of a segment, here's what you're going to do. You're going to check, does the segment contain an underfull edge? So you can see on the bottom here, I've marked one of the edges as red. I found an underfull edge. If there are many underfull edges, you just look for one. You only want to find a single underfull edge. And now you're going to fix it, meaning you're going to add it to H. And now you just repeat this. You go to the next segment, and in each segment, you look for an underfull edge. And if you find one, then you add it to H. So again, we found one, we added it to H. You go to the next segment, you look for an underfull edge. If you found one, you add it to H. And also, every time we add something to H, we also call remove overfull to make sure that there are no overfull edges. So for example, maybe in the next segment, we find an underfull edge, we add it to H, but now maybe the degrees in H are too high, there's an overfull edge, and so you remove some edge from H. So here, we removed an edge from the second segment. And you just keep doing this. Next segment, find an underfull edge, add it to H. But now eventually, you might reach a segment such that none of the edges in that segment contain an overfull edge. And now, this is the key point. At this point, you actually just terminate phase one, and you proceed to phase two. So now I need to show you that both of the properties in that red box above are satisfied. So the first property is automatically satisfied because we just always make sure that there are no overfull edges. So the second property is the hard part. So here's our key claim, which is that in this, when you terminate, then with high probability, there are going to be few underfull edges in G late. And the reason is actually very simple, which is that, remember, the stream arrives in a random order. And now this segment that you found contains a relatively large number of edges, and none of them are underfull. So this means that there must be relatively few underfull edges in the graph, because if there were a lot of them, then surely by randomness, one of them would have landed within your segment. So in particular, that segment contains like a 1/n fraction of the edges. So if it contains no bad edges, then there can be at most like n log n bad edges in total. Okay, so that's why we can terminate if we find such a segment. The only thing I've left to argue is, how do we know that we find such a segment? I mean, the bad case would be that we just, every segment you find an underfull edge and you keep going and you finish G early and you never found such a segment. So how do we prove that this algorithm actually terminates within G early? In particular, I'm going to claim that within n beta squared plus 1 segments, you're definitely going to terminate. And because of how we chose our segment sizes, basically within n beta squared plus 1 segments, you're still going to be within G early. So this shows you're definitely going to terminate within G early. And here's the argument. And it's basically similar to the greedy construction I told you before. I mentioned before that if you just keep fixing violating edges, then every time you get a little bit closer to having a regular degree subgraph. And so after n beta squared fixes, you actually will have a regular degree subgraph, and you will never find a violating edge again, because a regular degree subgraph, automatically all edges are satisfied. And so the point is, in each segment, you fix some edge. So you make a little bit of progress towards having a regular degree graph. And so you can't fix more than n beta squared edges before you stop. So there are most n beta squared segments where you fix something, and after that, you're definitely going to find a segment where you don't fix anything at all. And then you can terminate the phase. Okay, so that's the whole algorithm for phase one. And then again, phase two is simple. You just go through all of G late and gather all the underfull edges. And then you take your subgraph H and all your underfull edges together, and you find the maximum matching in them. So to quickly conclude, we showed an algorithm which gets a 2/3 approximation n log n space. And this is sort of the best of both worlds of the previous work. And it's also the first result to show a provable separation between computing and matching in random order streams and in adversarial streams. Let me finish with some open problems. So the first is, can we do better than 2/3? So as long as we use an EDCS approach, EDCS can only get you 2/3. So we're going to need some new ideas here to do better than 2/3. The really exciting thing would be, can we actually get a 1 minus epsilon approximation algorithm in random order streams? And it's unclear whether this is possible. So it'd also be interesting to have a lower bound showing that actually this is not possible. So finally, I want to note that these open problems, we don't even know how to solve them in the much simpler model of one-way two-player communication, but with a random partition of the input. So the random partition corresponds to the random order streaming. So basically, you have your graph, you split it randomly between Alice and Bob, and now Alice wants to communicate n bits to Bob, and Bob needs to reconstruct a large matching. We don't really know what the right upper and lower bounds are for that problem, so that would be an interesting place to start. Okay, and that's it. That's my whole talk.